Hi, my name is Naga Jahnavi, and in this presentation, I'm going to walk you through Ukkonen's algorithm, which builds suffix tree in linear time. So the agenda for this presentation is as follows. First, I'm going to discuss some basic terminology that will be helpful in understanding the algorithm in detail. Then I'm going to walk you through the naive order of M cube algorithm. Then we discuss the concept of suffix links, which helps in improving the time complexity to order of M square. Then we are also going to look at certain tricks and simple observations, which will lead to the linear worst case time. So let's get started with the basic terminology, and I'm going to cover these four terms, that is implicit suffix tree, true suffix tree, suffix link, and suffix extension. At first, let's look at what is an implicit suffix tree. So an implicit suffix tree is for a particular string s is obtained from the suffix tree of s by following three steps. In step 1, we remove every copy of the terminal dollar symbol from the edge labels of the tree. And as a result of step 1, we could encounter certain edges which don't have any labels, and hence those edges have to be removed. Also, we could encounter certain nodes which do not have at least two children, and such kind of nodes also need to be removed. Let's see an example of how to build an implicit suffix tree if we are given a suffix tree for a string. So here in figure 6.1, we see the suffix tree for string XABXA dollar. So let me walk you through how we can build the implicit suffix tree for this. So as part of step 1, we first remove all the terminal dollar symbols. Then as a result, you can see that this particular edge is not having any label. Hence, in step 2, we remove all such edges. Also, we see that this particular node will not have two children after the removal of this particular edge. Hence, this also needs to be removed. And same applies for this particular node. And that way, we obtain the implicit suffix tree for the string XABXA, which is represented in this figure 6.2. Now, let's move on to the next slide. That is, here I'm going to discuss what a true suffix tree is. A true suffix tree is a compressed trie of all suffixes of a string, and each suffix is represented by a unique path from root to a distinct leaf node. So, the important observation here is that a true suffix tree is something that is going to have a distinct leaf node for each particular suffix, whereas an implicit suffix tree may or may not have a distinct leaf node for a particular suffix. Then we are going to discuss about suffix link. Suppose we have an internal node V with path label X alpha, where X represents any single character and alpha is any substring, and it could possibly even be empty as well. And also there is a node S of V in the tree with path label alpha. Then here notice that alpha is a suffix of X alpha, and hence suffix link is something that joins node V to S of V. Let's look at an example to get a better understanding. For example, here in this picture, you can see that these red color arrows represent suffix links. Suppose this is the node V, and this particular path represents X alpha. That means here X is representing the single character X, and alpha is the substring. Here it is only of length 1, and that is A. And here we have, this is the node that represents S of V, and it has path label A, that is alpha. Hence, the suffix link is something that is connecting this V to S of V, right? Also, if we consider this as node V, then in that case, this will be the edge label. And here X alpha, in X alpha, this A represents the single character, and alpha in this case will be an empty string. And in when alpha is an empty string, the suffix link will point back to the root. Next, we are going to look at what a suffix extension is. So a suffix extension can be described as if we already have a path in the tree which is labeled S, J to I, then suffix extension is nothing but extending this existing path to include the next character which is at position I plus 1 to ensure that S, J to I plus 1 is in the tree. And while extending the existing path to include the next character, we could possibly encounter three different scenarios, and each scenario contributes to a different extension rule, which we are going to look at. And all these extension rules actually take only constant time. Suffix extension rule 1. In rule 1, we are going to encounter a scenario where beta, that is the existing path, comes to the end of the edge label of a leaf. And this is a simple scenario. What we can just do is append the next character, that is S of I plus 1 to the end of the edge label at that leaf. That is suffix extension rule 1. Then in suffix extension rule 2, this applies when beta either ends at an internal node or it could possibly end somewhere in between an edge label. And and after the end of beta, we don't find any path that starts with the character S of I plus 1. This is the scenario where suffix extension rule 2 comes into picture. And in order to deal with this, we first look at the case where beta ends with an internal node. When beta ends with an internal node, the what we have to do is quite simple. Just create another leaf edge, label it with S of I plus 1 and attach it to the internal node. Whereas the case where beta ends somewhere in between the edge label, in that case, we see that at the end of beta, now the paths are going to split. In that case, we need to create a new internal node at the end of beta, and then from that internal node create a leaf edge with label S of I plus 1. Those are the two scenarios we are going to see in rule 2. Then suffix extension rule 3. This is the simplest of all the suffix extension rules, where we already have what we want in the tree. Hence, we do nothing here. That means after the end of the path beta, we already see a path that starts with character S of I plus 1. That means we already have what we want, and hence we do nothing in this case. So let's see examples for all the three suffix extension rules with this. So in figure 6.3, we have an implicit suffix tree for AX, ABX. And now we are going to extend all the suffixes of this to include the character beta. Sorry, B. In this case, first let's consider AXABX. Now AXABX is the ending at the end of a label at the leaf. Hence, in that case, we can just append B to the end of that leaf label. Then the same applies for XABX. XABX also comes under rule 1 scenario, hence we append B here. Then ABX is also ending at a leaf, at the end of a leaf. Hence we just append B. Then BX also rule 1 scenario. Then X. Yeah, here is where rule 2 comes into picture. We see that the path is ending somewhere in between the edge label. That means rule 2 comes into picture. Here, when we need to create a new internal node and then create an edge, leaf edge labeled with B. This is the rule 2 scenario. Next, we need to just append B as well. And we see that already a path with B exists in the tree. That means rule 3 applies here and we don't do anything for this. This is how we obtain the extended implicit suffix tree after the addition of the character B. Then now I'm going to walk you through the naive algorithm which takes order of m cube time. So the first step is to construct the tree I1, that is implicit suffix tree in the first phase. That is, phase 1 is only the first character in the string, and then that is very simple, that you just need to create a leaf edge labeled with the first character, and it takes constant time to build the first implicit suffix tree. Next, the algorithm proceeds in m phases, that is I running from 1 to m minus 1, and this I represents the current phase. So in phase I, we are going to create an implicit suffix tree for the prefix of the string ending at position I. And how are we exactly going to build an implicit suffix tree in a particular phase? Suppose let's consider phase I plus 1. In phase I plus 1, there are going to be j extensions where I plus 1 extensions, and j runs from 1 to I plus 1. And in each extension, what we are going to do is we are going to we are going to walk from the root along a path represented by the path label S from j to I. So one thing we can be sure here is that in phase I plus 1, we already have the implicit suffix tree which was built in the previous phase II. And this II will contain all the paths uh, of the suffixes ending at position I. Hence, we are sure that S from J to I already exists in the implicit suffix tree ending at position, which was built in phase I. So we can just walk from root to find the end of this path, and then simply apply the suffix extension rules to add the next character I plus 1 to this path. And if we look at the analysis, we are sure that each phase here, if we do this walking from root to find the path Sj to I naively, then each phase is going to take I square time, and I goes from 1 to m minus 1. That is, there are m such phases. Hence, the time complexity will be order of m cube here. As we can see here that this particular step is taking is causing the time complexity to become m cube. Hence, can we find a way where we can optimize the step? That is, we can reduce the amount of work that we do from the root to find the end of the path with label S of j to I. So the answer is yes, we can actually do this with the help of suffix links. Suffix links will help us in a way they are shortcuts. That is, instead of walking from the root, we will actually find an optimal way of traversing from the previous extension to the next extension. And these suffix links, along with certain observations and tricks, will help us in achieving the order of m square time bound. Let's see how they help us. So, in order to look at the analysis and how they help us, we first need to see how to actually build suffix links and what observations we can have. So, the first thing that we look at is lemma 6.1.1. What does this lemma say? if a new internal node V with path label X alpha is added to the current tree in extension J of some phase I plus 1, then either the path labeled alpha already ends at an internal node of the current tree, or an internal node at the end of string alpha will be created in extension J plus 1 in the same phase. That means we are currently in phase I plus 1 and we are performing extension J. And we have found the end of the path label X alpha. And applying suffix extension rules, we had to create a new internal node V. In this particular scenario, what this lemma is saying that when this happens, then already the tree has a path labeled alpha, which already ends at an internal node, or an internal node at the end of alpha will be created in the next extension in the same phase, that is in the extension j plus 1 in the same phase that we are in currently. But why is this true? We are going to look at the proof for this particular lemma in the next slide. So the proof is as follows. So we are in extension we are in phase I plus 1 and performing extension j in that, and we located the end of the path x alpha. And if we had to create a new internal node at the end of string x alpha, what can we say about what suffix extension rule we might have applied there? For sure, we must have applied suffix extension rule 2, because only internal nodes are created in suffix extension rule 2. And rule 2 happens when we already have when the path x alpha extends with some character other than s of I plus 1, right? That means it must have ended in somewhere in between an edge. And X alpha is continuing with some character C, and that is why we had to create an internal node and then add a new leaf edge with label S of I plus 1, right? So, what does that mean? What does it mean if X alpha is already continuing with a character C? Then that means that somewhere in a previous phase, some phase before us, not exactly the one preceding us, but some phase which happened before us, x alpha was extended with character c. That means that means alpha, the path alpha also exists in the tree and must also have been extended with character c in that particular phase which happened before us. So that means we can be sure that path alpha exists in the tree, and it must continue with character C, right? Although there can be a case where C and some other character might also be a continuation of alpha. So these are the two cases. So when alpha continues only with character C, what will happen? In the next extension J plus 1, we will again apply extension rule 2 to add S of I plus 1 at the end of alpha, and we will create a new node S of V at that point, right? Otherwise, if case 2 was the scenario, that means alpha continued with C and some other character other than S of I plus 1, then that means already the alpha split into two parts already. That means alpha ends with an internal node. That means S of V already exists at the end of alpha. Hence, the theorem 6.1.1 is proved in either case. Now, let's look at two corollaries that follow from this lemma. So, corollary 6.1.1 says that any newly created internal node will have a suffix link from it by the end of the next extension. This is true, right? Because uh, we have seen from lemma that either alpha already ends at an internal, or it will be created by the end of the next extension. So by the end of the next extension, we should be in a good position to actually create a suffix link from V to S of V, right? So that is what is stated here in this particular line. Next, what will be the last extension of any phase? The last extension of any phase is nothing but adding a single character. And adding a single character will never choose suffix extension rule 2, right? It either will be suffix extension rule 3 or rule 1. Hence, no new internal nodes will be created in the last extension of the phase. That means all the suffix links from internal nodes are known by the end of the phase I plus 1, and I plus 1 has all those suffix links. This is an important observation, right? Now, let's look at the next corollary. In any implicit suffix tree II, if internal node V has path x alpha, then there is a node S of V of the same implicit suffix tree with path label alpha. And this can be immediately implied from the lemma, right? If alpha should already exist in the tree or will be created in the next extension. So by the time the implicit suffix tree is created, we know that if x alpha exists, then alpha path should also exist in the tree. So these are the observations that will actually help us in analyzing and also understanding how the suffix links were actually implemented. Next, um, so utilizing these observations, let's see how we can do the first extension in any phase in building the implicit suffix tree of a in a particular phase. For example, I plus 1. So the first thing we can note here is that the end of the full string s of 1 to I, that means suppose let's take the implicit suffix tree which was built in the previous phase I. Then the end of the full string s of 1 to I, that means the suffix starting at 1 and ending at I in the implicit suffix tree in phase I, is the longest, right? Longest suffix. And it follows that that must definitely end at a leaf node. It cannot be a prefix of another suffix, right? That means it will obviously end at a leaf node. And because of that, we can actually keep a pointer to the first leaf all when we are building when we keep building the trees across the faces. We can always put a pointer pointing to the end, the pointing to the first leaf, and this will actually help us in doing the first extension in any phase in constant time. That is, in any phase, what we need is in the previous phase, whatever the s of 1 to I we have, we just have that endpoint already because of this pointer, and hence s of I plus 1 can just be appended to that leaf label by the suffix extension rule 1. Hence, the first extension in any phase is very simple, and it on always rule 1 applies there. Now, let's see how we can proceed to the second extension from the first extension. So, in the second extension, we already know in the first extension what is the end of the s of 1 to I, right? That was the longest suffix we had in the implicit suffix tree in the previous phase. So, we know what is the end of s of 1 to I, and let it be x alpha, and let v comma 1 be the edge that is leading to the first leaf, and let gamma be denote the edge label on that particular edge that is leading to the leaf node 1. So in the second extension, what we essentially need is the end of the path alpha, right? Because in the first extension we had x alpha. Now we just need to remove the first character. Now we need 2 to I. That means just alpha, the path ending with alpha. So what we can essentially do here is, mm, we can actually walk up one node, that is to V. We can walk from leaf 1 to node V, just one hop upwards. And then we can be sure that V is an internal node, and definitely it will have a suffix link, right? Just traverse that suffix link from V to S of V. And since we walked up, then the path along which we walked up must be gamma, right? So from S of V, we again need to walk down the path labeled gamma to find the end of alpha. So this way we are actually optimizing it, right? Before we were actually walking from root to the end of alpha, but whereas now we are only walking from S of V downwards. So definitely this is some optimization, but how much is it helping us is something that we need to determine. And once we find the end of alpha, we can just apply the suffix extension rules. That is how we do the second extension. Now, in general, for any extension now greater than 2, what we can do is same, right? Uh, we if we are lucky enough, we will directly find. So what will happen is that in the previous extension we already we already must have found s of j minus 1 to I in the previous extension. So if we are lucky enough, at that end point we will have a suffix link, and that will directly complete our job. We just have to traverse that link, and no down walking will be required there. But in case if there is no suffix link at the end of the this particular sj minus 1 to I in the previous extension, then even in that case we just need to move one hop upwards to the to find an internal node that has a suffix link. So when we walk up one node, we could sometimes encounter root, or we could find an internal node that has a suffix link from it. In case if we found the root, then we need to walk down the root to find the end of the path that we are looking for. Otherwise, if we find an internal node, then we will have a suffix link already, and we just can traverse that suffix link to go to S of V. And now, whatever the upwalk we have done, the label along that, let it be gamma. And now, from S of V, you need to walk downwards along the path labeled gamma to find the end of S of J to I. And once we found the end of S of J to I, we can just apply a suffix extension rules to extend the suffix to S J to I plus 1. So somehow these suffix links are helping us in creating shortcuts for us. And how is this helping us, and how much it is helping us is something that we need to see. Now we have everything consolidated here, what we discussed till now, that is a single extension algorithm. So that is how we move from one extension to the next extension and perform it. So just let me briefly walk you through once in this consolidated information. That is, in the previous extension, we already must have found sj minus 1 to I, and that means this must already have a suffix link from it, or we can just walk one node up to find an internal node that has a suffix link. And once we have found it, we can just walk down along the path gamma to find the end of sj to I. So once we find the end of sj to I, we can apply any suffix extension rule that is applicable to that, and extend to add the character s of I plus 1. And in case if a new internal node was created in the previous extension, then now we must be in a good point to create the suffix link, right? So just create the suffix link w comma s of w here. This is the single extension algorithm that we have. Now, let's proceed to see an example here. That is, for example, in the previous extension, we came till here to find S of j minus 1 to I. That means um, now we need to find S of j to I, right? So in order to do that, um, what we can just do is we can, since this does not have a suffix link ending here, then we just need to walk up once to find an internal node that has a suffix link, and hence we just traverse this suffix link once to come here. And now once we are at this suffix link, whatever we have walked up, now we need to walk down, right? So we just walk down along the path to find the endpoint of gamma. That is where we find S of j to I, right? Or if it is phase I plus 1, then we find S of j to I plus 1. And sorry, we find S of j to I and then extend that S of I plus 1 character to the end of this. Now, in order to determine how much these suffix links have helped us in reducing the time complexity, we need few observations. That is, the first thing that comes is the skip and count trick. So once we have traversed the suffix link and came to S of V, we know that that is an internal node and has multiple paths emerging out of it. But do we have or but a simple observation here is that the starting character of gamma, let it be C. Then out of the emerging paths, there is only out of S of V, there must be only one path that starts with character C. So we can choose that edge, and we are sure that the subtree S of V will contain the path gamma in it, right? So once we found the correct edge starting from S of V, then we need not compare any further characters on that particular edge, right? We can just skip to the destination node on that edge, and then again from that point we find a valid path emerging out of it, which starts with the valid character that we are looking for. Hence, this will help us in instead before we were actually trying to compare each character of gamma to on the path. Instead, now the time will become proportional to the number of nodes on the path, right? Now this is the example that is illustrating that fact. So when we are trying to walk down from S of V to find the endpoint of this gamma path, what we can do is, at first we know that the first character is Z, and out of this emerging paths we have only one path, this starting with Z. Hence we can choose this, and we know gamma already exists in this tree, so we need not compare any further characters in this. We then skip to the destination node on this edge. Now from here we have multiple splits here. Now, ZA is something we already have. Now we need to check B. Now only this edge starts with B, hence we choose this, and we don't have to compare any other characters on this edge. Hence we skip to the destination node here. And once we skip to the destination node again, we are here. Now we need to look for D. Out of the possible paths starting here, only one edge starts with D. Hence, we take this, and we need not compare any other characters on this edge. Hence, the this part is done. We skip to the destination node, and hence now we need to look for G. Out of the possible paths, we know that only this starts with G. Hence, we skip to. Okay, so here you observe that GHY is has length less than whatever the edge label we have. So Instead of skipping to the destination node, we skip to the third character starting from this edge label to find the end of gamma. And then at this point, we apply suffix extension rules for this particular extension. So in this way, instead of comparing each character, now the time is becoming proportional to the number of nodes along this path, right? That is an important observation that we have. Now, now let's proceed to the next one. Now we have a lemma that says let v comma s of v be any suffix link that we have. That means any suffix link that we traversed, then at that moment, what we say is that the node depth of v is at most 1 greater than the node depth of s of v. And why is this true? And how is this true? This is what we look in the proof. Suppose we have let's consider any internal ancestor of v, right? Now, since V has some label X alpha path label, let's assume this internal ancestor of V will have some label X beta. Okay. Now this X beta will be a prefix of X alpha, right? And and definitely, since it is an internal node, it must be having a suffix link. And since the suffix link will take to another internal node that will have path label beta, right? Since because this internal ancestor has path label x beta, the suffix link will lead to an internal node that will have path label beta. Now we know that x beta is a prefix of v. That means in the same way, we know that beta will be a prefix of alpha, right? Sorry, prefix of alpha. Yeah, alpha is the path label of S of v. And hence, that what does that mean? The suffix link from an internal ancestor of v is leading to is pointing to an internal ancestor of S of v, right? And except one case where suppose if we have an internal node at the end of x, in that case the suffix link will point back to the root itself. Except that scenario, for every other internal ancestor of v, the suffix link will go to an ancestor of s of v. And since the node depth of any two ancestors of s of v must differ because they're on the same path, they cannot have the same node depth. And hence, each ancestor of v has an s suffix linked to a distinct ancestor of s of v, right? Hence, it is proved. Except, hence it is proved, right? So let's look at it with the help of a diagram, which will give more understanding. So here you can see, suppose if x has an internal node at the end of it, that means the suffix link will point back to the root itself, except that all other ancestors of v will have suffix links pointing to ancestors of s of v. That means the node depth of v is at most 1 more than the node depth of s of v, right? Suppose if there was no internal node at the end of x, then that means the node depth of will be equal to a node depth of s of v. If there is an internal node at the end of x, it will be 1 more than the node depth of s of v. Hence, the conclusion is that node depth of v is at most 1 more than the node depth of s of v. Now we are in a good position to do the time complexity analysis based on what we know, using suffix links, skip and count trick, and the lemma that we studied just now. So in any extension, we are at most walking up one hop to find the nearest node with suffix link. So that upwalk will at most decrease the node depth by 1. And the suffix traversal, we are moving from V to S of V. From the lemma we learned just now, we know that node depth of V is at most 1 more than the node depth of S of V. Hence, at most, the when we traverse a suffix link, the current node depth can reduce by 1. It may or may not, but if even if it reduces, at most it reduces by 1. And once we find S of V, we perform some downwalk from there. And when we move down, we are increasing we are moving to a node of a greater depth, right? This is what we know. Then, what we can conclude from this, considering a particular phase, we can have at most m extensions, right? In And we know in an extension we decrement the node depth twice. That is, once if we move up, and if we traverse a suffix link, at most one node depth will decrease. Hence, across m extensions, we can reduce the current node depth by 2m. And also, we know that the no node can have depth greater than m, right? It cannot be more than m. The size of the string is itself m, so it cannot be more than m. That means, how many times can we actually increment the current node depth? The number of increments will be bounded by 3m, right? Because we are decrementing only 2 times, and the max we can go is m, when the node depth can't increase more than m. Hence, it is the number of increments is bounded by 3m. And we know from the skip and count trick that one node skip can be done in constant time. That is, during the downwalk, each node skip can be done in constant time. Hence, in a particular phase, the amount of downwalking is order of m, and applying suffix extension rules is a constant time operation. Hence, each phase will take m time, and we have m phases. Hence, the complexity will be m into m, or order of m square. So now that we have established a time complexity of order of m squared with the use of suffix links and skip and count trick and the lemma that we have studied before, now we also look at few more simple tricks and observations, and we will then analyze the complexity beyond the boundaries of the phases to attain the linear time complexity. So let's proceed further. So the first thing that we see now is the edge label compression. In edge label compression, what this says is that instead of representing an edge label on each edge with the string of characters, we can actually store the starting and ending index on that edge. This will help us with a great optimization on the space. That is, the edge label before was variable in size. Now we have a constant number of things to store, just the start index and the end index. This will help us in optimizing the space, and as well as that we have another use of this. One of the major improvements in time complexity comes from this trick. That is, there are certain implicit extensions that we do as part of extension rule 1, as we will see in the further slides. As part of that, um, when we have extension rule 1, that is, when we encounter the end of a leaf, we just have to add a new character, right? So if in case if we store the end of the edge leaf label with a variable e indicating the global index, and if we increment that global index once per phase, we will be able to do certain implicit extensions in a phase in constant time. That will bring about one some of the major improvements in the time complexity and will contribute greatly at the end to attain the linear worst case time bound. So as we can see in this example, uh, for example, if we consider this particular edge A, B, C, the starting index is 1 and the ending index is 3. That means this particular edge is being represented by the starting and the ending indexes in the particular string. This is what is the edge label compression is. Next, next we are going to have another observation here in the slide, that is, which says that rule 3 is a showstopper. What does this mean? So, in any phase, if suffix extension rule 3 applies in extension j, it will also apply in all further extensions j plus 1 to I plus 1 until the end of the phase. So, essentially, when does rule 3 apply? Rule 3 applies when what we want already exists in the tree and we don't have to do anything else, right? That means that means for example, if we are in phase I plus 1, then essentially in extension j, what are we trying to do? We are trying to find out the path s j to I, and we want to extend it with I plus 1. But when suffix extension rule 3 applies, then that means the end of the path sj to I already continues with I plus 1. Then what can we infer from this? What we can infer is that if this already exists, then it means somewhere in a previous phase, somewhere before, not necessarily the immediate previous phase, it could be any phase before, we extended s of j to I, the path labeled s of j to I, with s of I plus 1. That is why it already exists at this point. That means at that particular previous phase, it must also have extended s of j plus 1, the path s of j plus 1 to I with s of I plus 1, right? It must also have extended this path, which is a suffix of this, with s of I plus 1. Then this inductively applies to j plus 2, j plus 3 until I plus 1. That means suffix extension rule 3 inductively applies till the end of the phase. So, what does this mean? What can we do based on this? So, once in any phase we apply rule 3, we need not do any other work in the phase. So, that is where we arrive at trick 2, that is, end any phase the first time that the rule 3 applies. This is a very important observation. Now let's proceed to the next part, that is the observation 2. Observation 2 says that once a leaf, always a leaf. Why is this so? For example, a leaf is created and we have suppose let it end with um, suppose it has some label alpha, and under paths before it some, let it be beta. So basically it has path label beta alpha, and the leaf node has edge label as alpha. Now, in whenever you want to extend this leaf, that means you when you want to apply extension rule 1, you when you come to the end of the leaf, there is no way you can create an internal node here, right? So extension rule 1 will never create any internal node or create any splits at this point. It just appends the next possible character to this it just appends it to the end of this edge label. Hence, once a leaf is formed, it will always remain a leaf. So if at some point a leaf is created and labeled J, then that leaf will remain a leaf in all the suffix trees during the algorithm. Now let's proceed to the next one. So if we examine the the sequence of extension rules that we apply in a particular phase, we will observe a pattern. That is, first we will have a sequence of extensions where we apply extension rule 1. Then we will have then we may or may not have certain sequence of extensions where rule 2 applies, and we may or may not have one extension that where rule 3 applies. And if we have, then that will be the last extension that we will be doing in that phase, because after that we know we don't have to do any other work based on the observation which we just saw previously. So, and one more thing, the first the first extension in any phase will be will start with extension rule 1, because we know, suppose in phase I, we know that we have the implicit suffix tree for I minus 1, and that means we already have the path s of 1 to I minus 1, which ends at a leaf node 1, right? And that means there we are applying suffix extension rule 1. Hence, the starting extension will always start with 1, followed by there will be some number of extensions with rule 1, then with rule 2. Why should this pattern even occur? If we think about this, let me explain. For example, when does a rule 2 apply? For example, we have some path with, let's say, x alpha. Okay. And now when we when we when do we apply rule 2? When the path is a prefix of an existing suffix, right? When it ends at somewhere here, either at an internal node or somewhere in between an edge. Let's assume it and at some point we want to extend the end of the string from this point with extension rule 2. Then in that case, let's assume that this part is x beta, right? So by the time we want to extend this part, we already know that x alpha is in the tree. Then that that means this one was created in the previous phases. That means alpha must also exist in the tree, right? If alpha also exists in the tree, then what does that mean? Um, so in the current extension, we are trying to extend this. Let us assume it is the jth extension. Now in the j plus 1th extension, we will try to find the end of beta. Now we know that x beta is a prefix of x alpha. That means beta is a prefix of alpha. That means beta will be a prefix of another suffix again. And hence, rule 2 will apply again in the next extension. Hence, what we can infer is that this pattern holds true. That is, first we will have a sequence of extensions having extension rule 1, then a few extensions with extension rule 2, and possibly at the end an extension with rule 3, and after that we stop. Or we could keep doing this extension rule 2 and we could end the phase as well. I mean, if we don't encounter a rule 3. So this is how the pattern applies. Now, next few observation is that these this chunk where we are actually applying extension rule 1, these are the leaves which are already existing in the tree. We are just appending the character to the end of the edge labels at those leaves. So these leaves come from phase I minus 1. Then here in when we apply extension rule 2 here some number of times, in extension rule 2 we actually create a new leaf edge with s of I plus 1 as its label. That means we are creating a new leaf. Here we are getting new leaves, right? And all of this, the existing leaves and also the new leaves, will become the leaves for phase I plus 1 where extension rule 1 will be applied, right? And then we will have some extensions with rule 2 and then a possible extension with rule 3. So what we can do is that if in phase I, let ji denote the last extension where this sequence of 1 and 2's apply. Then this will actually map to the last extension in which rule 1 will apply, right? That means extension rule 2 can, that means all of these will actually become the implicit extensions. Implicit extensions are actually something for which we do not explicitly do any work. They just can be done constantly in constant time. We will see how these um, extensions with rule 1 become implicit extensions and can be done in constant time in the phase. So basically, these will be the implicit extensions. These will become the explicit extensions where we are actually explicitly doing some work. Explicit extensions where we are actually doing some work. So basically, if we store this as ji, then this will map to the last extension in which the rule 1 applies in phase I plus 1. And we also know this will be the last explicit extension that we are doing in phase I. That means we know the end of the path where this extension was made, right? And that will become the first explicit extension that we will be doing in the next phase. So hence we can actually start the explicit extension work in the next phase directly from what we have stored before, right? Also, if one more thing to note is that if this is ji, this will be ji plus 1. This means what we can see is that ji is less than or equal to ji plus 1. Why is this so? Because already these are contributing to the extension 1, the number of leaves, and possibly we are doing a few more extensions with rule 2 in the second phase. That means ji will be less than or equal to ji plus 1, right? So the number of leaves from one phase to another will increase, but never will either remain the same or increase, but they will never decrease. So these are some of the important observations that we make. Now here comes the trick 3, how we do the extensions with rule 1 implicitly in constant time in a phase. That comes from the edge label compression, what we noticed, where we are labeling the leaf p of I plus 1. I mean the ending index on a leaf edge. Instead of writing the end index explicitly, we can actually represent the end index with the help of a variable e, and e will be the global index and will be incremented in each phase. So what happens when you increment e by 1 in the in a at the beginning of each phase? That means you're just incrementing the end index of the leaf at the beginning of the phase. That means you're doing all the rule, all the initial extensions where rule 1 applies in constant time in a phase. That is what trick 3 says. Next, yeah, here we come to the single phase algorithm. So how we do a single phase? Um, First, we just increment the index e to I plus 1. That means here we are doing all the rule 1, all the extensions with initial extensions with rule 1 in constant time. Next, in the second phase, sorry, in the second step, where we come across the extensions where rule 2 applies. So uh, we know that from rule 2, whenever that applies, we can follow a trail of suffix links. That is just walk up one node, suffix link, and then some down walk. So this we can do for certain number of times where rule 2 applies, and once we encounter rule 3, we are done with this phase. And also we start this the extension with rule 2 at the point uh, where the previous phase ji has stopped, right? From that point we continue in the next phase. Hence, you're starting at ji plus 1 and until reaching j star where rule 3 applies. And then for the next phase, ji plus 1 will be set to j star minus 1. The time complexity analysis based on the suffix links, tricks 1, 2, and 3. So the time complexity now is analyzed differently. That is, we look across beyond the boundaries of the phases, and we calculate the analysis for the implicit extensions across all the phases, and also the time for explicit extension across all the phases. So first, let's consider the implicit extensions. For implicit extensions where extension rule 1 applies, we are just doing a constant time work of incrementing the global index. Hence, for a phase, then the time taken for an implicit extension is constant, order of 1. And we have m such phases. That means the implicit extension work takes order of m time over the entire algorithm. Then, for the explicit extensions, What are we doing? Let's consider J dash corresponding to the current explicit extension that we are doing. We know that J dash never decreases as we have seen before, and it does remain the same between two successive phases when we're transitioning from one phase to the other. And in a particular phase, it could increase, but it never decreases. Hence, we have M phases and J dash is bounded by M. That means we only have 2M explicit extensions. Now, now for these explicit extensions, we walk at most once to the previous hop or the node, then traverse a suffix link and then walk down. We know that when we move up or take a suffix link at most in an explicit extension, the node depth could decrease twice in an extension, in an explicit extension. And during the node, when we are walking down from S of V, the node depth increases. Hence, since we have two M explicit extensions, and for each explicit extension, we can at most reduce the node depth twice. And we know that the maximum node depth is bounded by M. That means how many times we can increase the depth, how many increments we can have. We can only have around approximately 5M increments, right? That means it is bounded by M. The total time taken for all the node skips across, for all the explicit extensions across all the phases takes order of m time. That means it is linear, and hence that is how we attain the linear time complexity in Ukkonen's algorithm. Now, we also see that at the end of phase m, we are actually creating the implicit suffix tree im. But what we need is a true suffix tree, not an implicit suffix tree. Hence, we need to convert the implicit suffix tree to the true suffix tree. In order to do that, we just need to add a terminal symbol. We just need to add the terminal symbol dollar to the end of S and execute another phase of the Ukkonen's algorithm. Then after that, we can just traverse the tree once, apply some BFS or DFS, traverse the tree once, and then replace all the global indexes at the leaf edges with M. This takes order of M time. Hence, Ukkonen's algorithm builds a true suffix tree for the string along with all its suffix links in order of M time complexity. And yeah, thank you.